All right, so thank you all for coming to the ANU Mathematics Society's first talk in our seminar series. I would like to start by acknowledging the traditional custodians of the land on which the ANU is situated, the Ngunnawal and Ngambri people. Pay my respects to their elders past, present and emerging. And I'd like to also give a thank you to the executive who helped to get this event running, especially Corey DeWitt for their work. Without any more time to waste, I'd like to invite Dr. Joan Licata to begin what looks like it'll be an exceptionally interesting talk. Thank you.
Okay, well, thanks so much for the invitation. It's really fantastic to get a chance to chat with you all. It'd be lovely if we could all be in a room together, but barring that, it's great to see some familiar names in the list. And some of you have seen this room before over the last year, but for those of you I don't know or haven't seen in a while, I'm Joan. I'm a lecturer here at the ANU. My research area is in low-dimensional topology. And what I wanted to tell you is sort of a fun story about a topic that creeps from very concrete calculations, including some vegetables, into some areas of low-dimensional topology. So this is really not a class. It's not just that there won't be assessment, but I'm just going to tell you a story. So I'm going to give myself permission to tell you some lies along the way. I don't have very many details. It's meant to be fun. And by all means, interrupt me at any time with any questions. So maybe I'll just go ahead and dive in. I should also give you a heads up that there's a 9-year-old dressed like Mo Salah playing hallway soccer behind me. So I can't guarantee we'll be free for interruptions, but we'll do the best we can. So. Okay, my talk is on Kale and Crochet and Gromov hyperbolicity. And what I want to start with is the idea of smooth surfaces. So when I said I'm just going to tell a story that's not a proper class, part of what I mean by this is I'm going to give myself license to not really define things properly. So those of you who've taken differential geometry may have a very refined idea of what I mean by a smooth surface. And if you haven't, you're probably picturing the right thing. So when I say smooth surface, let me tell you the kinds of things I'm thinking of. I'm thinking of things like spheres. I'm thinking of things like a torus, so the surface of a donut. I'm thinking of more interesting things like what you'd get if you took 2 donuts, shoved them together, glazed the whole thing, and then removed the donut, just leaving the glaze. So these are the kinds of things I mean by smooth surfaces. And when I say they have geometries, what do I actually mean? Well, I'm going to try to get to that. And at some level, saying they have geometries doesn't have a whole lot of content until we get there. So let me just pose that we're going to say that triangles are a geometric feature, and these shapes are going to have very different kinds of triangles. So what do we mean by a triangle? Well, for us, a triangle is take 3 points and then connect them by 3 paths. Now, this is the kind of triangle we would get. Let's see if let's have fun with color. This is the kind of triangle we'd get if we were working in, say, the plane. And the plane is not one of the surfaces that I drew above, but in fact, this is the same kind of triangle you'd get if you put it on the surface of the torus. And so when I say different surfaces have different geometries, mostly I'm secretly thinking of surfaces without boundary, like these ones on the top row. But if you're happier thinking of a surface as the plane as R2, then in fact thinking about what happens on the torus is just fine. So one of the things that you sort of show very concretely in algebraic topology is that a torus is basically just a plane that's been rolled up. So if you take your big plane, this is my plane, and you roll it up in one direction, you have a cylinder. And somehow the distortion in the geometry that we get by rolling it up isn't that significant, okay? And then if I had better paper, I could put this together to make a torus. And we don't lose much of the geometry of the plane when we do this. So let's give a definition of a triangle that's going to work in more general setting. And so for us, a triangle is going to be take 3 points in your space. So we assume a space has points. We're going to be pretty general later on, but for now we assume space has points. And we're also going to make an assumption that if we have 2 points in our space, that we can connect them by a path. So what I'm saying doesn't apply to all possible spaces, but it's a reasonable thing to impose. So let's suppose that we have a whole bunch of different paths to connect 2 points. We have to have some way to measure the length of the path. And assuming we can measure lengths of paths, we'd like to have some notion of finding a shortest path. Okay, and as long as we're willing to stipulate that such a things exist, which imposes some conditions on our space, then we have a notion of a triangle. Okay, so what's an example of a triangle? Let's keep going and see some interesting ones. We'll start with triangles in flat surfaces because these are the things we really understand well. So in a flat surface, you can think of this as R2. There's a lot of things we know about geometry. So first of all, we know that triangle edges are line segments. Okay, we know that 2 points uniquely define a line. That says uniquely define a line. We know lots of things. What else can we say? We say 2 lines are either parallel or intersecting 1 point. And a whole bunch of other things that date back to Euclid. So I imagine we could generate a lot more ideas in these lists, but it turns out that many of the things we could come up with here are going to be features of the fact that a plane is flat. And what we're really going to be interested in is the things that aren't flat. So let's look at some other examples, okay? So what we want to think about next, and this is our first new idea, is the idea of curved surfaces. And a sphere is going to be our example of a surface with positive curvature. And let's start by trying to figure out what a triangle in a sphere looks like. So I'm going to put some points on. I'm going to put a point at the North Pole. I'm going to put some points on the equator. Okay. And as many of you probably have seen before, we know that if you have 2 points on a sphere, then the shortest path to connect them is an arc of the great circle that they lie on. So if I have this on the pole, I'm going to draw this in as sort of a line of longitude. Let's have fun with shading because I like my iPad. Okay. So this is my great circle. And if I want to keep track of building a triangle that connects those 2 points, we measure, there's 2 arcs. There's the one that sort of just lives in the northern hemisphere, and there's the one that goes all the way around. And so the shortest path connecting these 2 points is going to be this one. And similarly, let's put in our other one, the shortest path connecting these 2 points is going to be this arc of a great circle, and the shortest path connecting these 2 is the one right here. And if you look at these arcs on the circle, one of the things you can see right away is that we have something that's different than in the planar case. So one of the things, going back, one of the things I should have said is in a triangle, if we measure the 3 interior angles of a triangle, then the sum of the interior angles is pi. Okay. And I should have said that because that's the whole point of what we're trying to contrast here, is that on the sphere, the sum of the interior angles is not pi. Now, we have to decide how we want to measure angles, but if we think of this sphere as living in Euclidean space, then it's not so bad. So the sort of reasonable way to measure angles is the following thing. Let's take this curve in Euclidean space, and let's take the tangent line at that point, and let's take the tangent line along that curve. So we have these 2 pink curves. They each have well-defined tangents, and then we'll just measure the angle between the 2 lines. So that's a reasonable thing to do. If we want to say an angle between curves, we choose the best approximation of those curves by lines and then take the angle between the line. And what we see here is we're going to get a pi over 2 here, and a pi over 2 here, and a pi over 2 here. And in fact, the sum of our interior angles is greater than pi, and that's going to hold for every triangle on the sphere. So this is something intrinsically different about what's going on in the sphere than what we saw in the plane. Okay. And so when I said surfaces have different kinds of geometries, this is the kind of thing I'm getting at. Okay. So we can pause for a moment and appreciate the sphere, because after this, we're going to move to negatively curved surfaces and we won't spend any more time on spheres. So behold the sphere, and now I'll take it away. Okay, and so now we want to have a negatively curved surface, and here's my picture. Okay, I really wanted to try to find a Pringle. If we'd been doing this in person, I would have, but it didn't seem worth an extra trip to the shops. So this is my saddle. So this is supposed to be a saddle. I know a story about a mathematician from France, maybe, who was playing Pictionary one time, and he got saddle was the word he was supposed to draw in Pictionary. And it wasn't like a maths Pictionary game, it was just an ordinary one. And he correctly drew something like this. And he said, I have no idea what this means like in the real world, but I know that that's called a saddle. So you can picture this as just something you could graph as x squared minus y squared. Or you could picture this is a thing that's supposed to sit on the horse. So like if this is the horse, this is like the neck going up. That's the horse. There's the horse. And now some legs going down. So now you see why I'm a mathematician, not an artist. Okay, but we have a saddle. And what we want to do is try to think about what triangles look like in this saddle. And so we're going to play the same game. I'm going to choose 3 points on the saddle. Okay, and here you're going to just kind of have to believe my picture. So let's try to draw what these curves look like. And this is the shortest curve, and this is the shortest curve, and this is the shortest curve. And because I know what happens if you actually can do these computations, I can tell you that the picture I've drawn is something like this, where the sides kind of bow into each other. And so what we see is that the sum of the interior angles is less than pi. Okay, so for now, we're just going to take these as a definition. Okay, we'll say that if you have the kind of space where you can define triangles, then a space is positive curvature if the angle sum of every triangle is greater than pi. It's a flat space, like the plane, if this angle sum of every triangle equals pi, and it has negative curvature if the angle sum of every triangle is less than pi. And so our examples are sphere, saddle for now, okay, and flat. Well, we could have put down the plane, but in fact, just for fun, I'll put the rolled up plane. We have the torus. Okay, so we're going to spend most of our time talking about things with negative curvature. And the thing that's nice is that once we've turned this into a definition, we can find some other examples. So once we look at the triangles on different objects, one of the things you can find out is that a piece of kale has negative curvature. It depends on the kind of kale you have, but this kind of kale, and the idea is that you should think of the kale as some sort of step far down a sequence that starts with a saddle, okay? And then you can imagine, maybe you've heard of the monkey saddle. So this is the one where the outside goes up and down and up and down and up. Okay, so let's see if we can do this. I probably can't draw this. That's as you go around the edge. So our ordinary saddle goes up and down and up and down and up. The monkey saddle goes up, down, up, down, up, down. And that idea is that if you're sitting on a horse and you're a human being, you just have a leg on each side. So you need 2 places where it goes down. And if you're a monkey, you also need somewhere for your tail to go. So that's why it's called the monkey saddle. And then you can imagine putting more and more ripples in. So as you go around, you go up, down, up, down, up, down, up, down. And eventually you end up with something that's like a piece of kale. And so the idea is that if we measure, you put 3 points on your piece of kale, especially if you put the points out kind of near the edge, you're going to find triangles that curve into each other. Okay. Another one that shows up is this idea of crocheted coral reef. So if you're looking for a lockdown hobby, I've just put a link in the chat for a crochet pattern to make your own hyperbolic plane. So this is going to be a space that if you measure the lengths of the angles of a triangle that you put on your crocheted object, you'll get something that looks like this. You'll find out that the edges kind of come into each other, and you again have these triangles with angle measure less than pi. There's also some really fantastic pictures of crocheted coral reefs. Somehow this became a thing a couple years ago that mathematicians and marine biologists and crocheters got together and started doing this. So I don't know how to crochet. I can't make one of these, but you know, if everyone wants to make one and we host our own crocheted coral reef with a few side talks on hyperbolic geometry at the end of the year, why not? Okay, so let's keep going. Now, what I want to do is I want to say, I want to consider situations where instead of measuring my shortest paths by having an object sitting in Euclidean space and then putting a path on there and just measuring the space in Euclidean, the path in Euclidean space, I want to start working towards a way to measure things into the space itself. So let's think about how we measure lengths of paths. So what is the setup I have here? I have 2 points, X and Y, and I'm going to choose some path gamma between them, okay? And I think my gamma as a path from 0, 1 to whatever my space is, okay? So that gamma of 0 is X and gamma of 1 is Y, okay? And if I do this, then I have this path length in, oh no. Okay, hold on, sorry, there's supposed to be an extra slide in here. Give me just a second to quickly edit, hold on. Okay, you can't see that yet. There's supposed to be a second slide and it vanished. Okay, so this is how we measure the length of a path in ordinary life. we say there's this path length integral, and if we integrate gamma, the magnitude of gamma prime of t dt, then what we get is the path length. Okay, and so with the distance function we have is that we say for any path we can measure the length of the path, and we say the distance between x and y is the infimum over all of the gammas of this type, the length of gamma. Okay, now if you haven't taken analysis 1, you might 515 does infimums already, is that right? Everyone here knows what an infimum is? Great. Okay, so we have this distance. And now what I want to do, the big reveal is kind of ruined by my typo on the slide. Now what I want to do is I want to change how I measure distance. And the point is that everything I have written on this slide still makes sense. We define the distance between 2 points as the length of the shortest path between them, but I'm going to change how we compute the length of the path. Okay, so that's what we have now. Okay, so the point is, what does this do? Okay, and let's think about this. So for starters, we have to work in a world where y is not going to be able to be 0. So let's restrict to the upper half plane. So let's restrict to x and y such that y is greater than 0. Okay, and we're going to measure path length this way. So let's just think about what this could look like. Okay, here's my upper half plane, my x-axis, here's my y-axis, and we want to think about the consequences of this definition. So if I draw 2 curves like this, let's call this one gamma and this one alpha. Okay, which one of those curves is longer?
Should be the lower one, right?
Yeah, the lower one is longer, right? Because we assume we're dividing by something smaller. Up here, maybe whatever our y-axis is, we start by measuring it the normal Euclidean way, but it's divided by a factor that's constant along the whole thing. So here's a more interesting thing. Which of alpha and beta is longer? So let's even make it more interesting. Let's get a new gamma. Okay, let's do this for a second. Okay, what I've done is I've done 3 different paths that all connect points that from a Euclidean point of view are the same distance away. Okay, and so what have I done? If I were only using the Euclidean distance, then it's clear alpha would be the shortest one. But what I've done in beta is I've traded some extra ink for moving into a territory where I'm dividing by something bigger. And what I've done on gamma is I've traded even more ink for moving into a territory where I'm dividing by something even bigger. And so you could ask, what are you supposed to do? Is one of these paths, is there one that's actually shorter? Do they keep getting shorter as you go higher and higher up? Or at some point is the trade-off between how much ink you're writing down outweighed by how far away you can get to the axis? Okay, and so what we want to look at next, is there a question?
Yeah, I was just thinking, because you're dividing by y of t, if these are supposed to be sort of parabolas, then it depends on the...
Sorry, keep going.
That I was going to say, it kind of just depends on the coefficient of the parabola, right? Because the gradient will then sort of scale up by as much as how you're dividing and should cancel out. You could get a parabola-looking path that has the same length as alpha.
Let's even do this for a second. Let's even do something like that. So these are meant to be curves. So I appreciate the comment. These are meant to be curves which go up. I'm not claiming I'm drawing anything as precise as a parabola. In fact, what we want to do is we want to try to figure out what is the shape that minimizes the path, this path length. Okay, so you're right. We could, if I give you a path, an explicitly parameterized path, we can compute it, and we can see what we can get. And if I give you 2 different ones, you can figure out which one's shorter. And what we want to do is find out, is there an optimum? What is the actual shortest one? We want this infimum to exist, so we can say what the distance between 2 points are. And the question is, what kind of a path realizes that? Okay, so it's actually a really beautiful statement. Okay, and okay, so the last one is just not supposed to have a y on it. This is what we're saying, and we want to say what the actual shortest paths are. Okay, and there's 2 kinds of shortest paths we need to understand. So let's put some axes down again. okay? And the first kind of shortest path is sort of a nice one, vertical line segments. So if you have two points which are vertically aligned, the shortest path is actually just the line segment. But if you have two points which aren't vertically aligned, you get something really interesting, okay? Let's see what the limit of my drawing is here. What you get as the shortest path is you get the arc of the circle. Come on, iPad, don't do this to me. Take a circle that's centered, oh, that's pretty good. Take a circle that's centered on the origin, and the shortest path between 2 points is the arc of the circle that connects both of them and has its center on the origin, on the axis. So this is the shortest path between those 2 points. So your original question, which was, did you draw parabolas? There's probably a best one. The answer is there may be a best parabola, but if you have a parabola, you can do better if you replace that parabola by an arc of a circle. So it takes a little bit of work to figure out, but it's not too hard to see that any 2 points that aren't vertically aligned, in fact, live on a common circle. And this gives you a really cool picture of what the shortest paths are. So here's a picture of some selected geodesics, shortest paths, in the hyperbolic plane, okay? So great, there we go. We can just appreciate that for a second. We have a bunch of circular arcs. They didn't draw any of the vertical ones, so those are ones we can fill in ourselves. And now that we have some idea of what these paths look like, what my question is, what do the triangles look like? And in particular, are they triangles that tell us we have positive curvature, we have flat curvature, or we have negative curvature? And I think in this picture, I think all of the triangles, let's see if we can find a triangle. All of the triangles look like they're things with their with the vertex down on the axis, which is interesting in some context, but not what I want. So let's put in a new triangle. Let's put in a triangle that goes like this. So I'm putting in this geodesic, this shortest path, and I'm putting in this triangle and this triangle, okay? And if we look at this, it should at least look plausible that these are skinny triangles. It's a little bit unclear what's happening right here, but we can see that these ones are thin angles. And in fact, you can compute that all triangles have angle sum less than pi. Okay, and so now we can justify this up here. This is the notation for the hyperbolic plane. And hyperbolic is another word for saying negatively curved. Okay, so if I felt like doing some computations, we could now do all sorts of computations. We could do things like if you get 2 points, how do you actually compute the length of them from their coordinates? How could we actually compute the angle sum? How could we compute a notion of area in this geometry? But I don't really like doing computations, and I really don't like doing computations out loud. And the thing I like even less is if someone else does computations in front of me. So I'll say there's a whole bunch of fantastic resources. If you're interested in this kind of thing and want to read more about them, I'm happy to point you in the direction of some really cool books about it. But we're going to just go ahead and move on and say, where else can we find thin triangles? We have this nice concrete version of a hyperbolic plane where we get this negative curvature. And in fact, this is the kind of geometry that you see on the saddle, in a neighborhood of the saddle point. But we have this definition of a thin triangle. Is there any way to use that in any other place? And in fact, if we interpret what it means to be a thin triangle a little differently, we can get some more mileage out of this. Okay, so now I want to say what it means to be a thin triangle in a slightly different way. I'm going to put that triangle we have back on for a minute because it's a little helpful to have. So pretend that's an arc of a circle, as close as we get. Okay. So when we draw a sort of stereotypical thin triangle, we can think about what's happening near the angles, but we can also just think about what's happening in the middle of the sides. And the idea is that they're kind of getting sucked into the interior of the triangle. Okay, and this gives us our new way to characterize thin triangles. Instead of focusing just on those angles at the vertices, let's think about the edges. okay? And we say that a triangle is delta thin if each edge is contained in the union of the neighborhood of the other two. So let's see if we can do this. I'm going to try to draw, oh, this is not big enough. I want a fatter highlighter. Let's try this. Okay. I'm going to draw a delta neighborhood in pink around this edge. Okay. So that's one of my neighborhoods. And I'm going to draw a neighborhood around this edge. Okay. And so here what you're supposed to do is I say in the string, I'm looking at this distance here is delta. So from each point on the edge, I just take the whole ball of radius delta around that, and we do that, the union of those for all of the points on the edge. And so this one, again, this is like at this distance is delta. And what we notice, because I got to choose my highlighter size, is that this edge number 3, so we have edge number 1, we have edge number 2, and we have edge number 3. And edge number 3 is completely contained in the union of those pink and blue regions, okay? And if we get this right up above, we're going to see the same kind of thing. Here's my blue neighborhood of one of the edges, and here's my pink neighborhood of the other edge. And that third edge right here, this edge number 3, is contained in the union of those blue and pink neighborhoods. So what have we gotten out of this? One of the things to believe is that in the case of the hyperbolic plane, a triangle is going to be delta thin in this definition, if and only if it's going to have angle measure less than pi on the interior angle, on sum of any triangle, okay? That's, again, the kind of thing you can prove with some computations, but it should seem plausible, okay? And what's nice about this is this allows us to generalize the notion of thin triangle to settings where you don't have a notion of angle, okay? So we can now say that in any setting where we can measure neighborhoods of radius delta, that we can talk about whether triangles are thin or thick, okay? So let's just briefly notice that R2 is not delta thin, or is not delta hyperbolic, okay? So if you give me any delta, I can construct a triangle so that I can construct a triangle so that my third edge is not contained in the union of the other two. You could say, okay, let's make the delta bigger. Well, I can make my triangle bigger. Whereas if you do this in a hyperbolic setting, even as you stretch the vertices farther and farther away, it ends up sucking the edges in more and more, okay? So R2 is not delta hyperbolic, can make the triangles too big. Okay. H2 is delta hyperbolic. Okay. I don't remember what the constant is, but there's a pretty good decimal estimation of what the delta is that you need to make all the triangles in the hyperbolic plane work. Okay. And what this does is let us expand our notion to wider variety. So let me give you an example of a space where we can still have a notion of distance. We can still have a notion of a delta neighborhood of points, but we wouldn't be able to measure angles. Okay. So let's change gears very significantly. And I want to introduce what a graph is. So a graph is a pair, V comma E, where V is a set. These are the vertices. And E stands for edges. Okay. And E is a set of pairs of elements of V. There's lots of more complicated versions of graph. We're taking the really simple one. So here's an example of a graph. Okay. This is my set V, which I represent as dots. And this is my set E. I'm going to take some collection of subsets of pairs. Okay, now this is a really kind of simple graph. There's lots and lots more complicated ones. There's fantastic theory of combinatorics and algebraic properties of graphs. If I draw the thing where I connect all of the edges, this is called a K5. It takes all of the pairs of edges. So here we take all possible sets, pairs are in E. And I will say I'm only going to be interested in connected graphs. So I'm not going to be interested in the case where maybe some of my points are like this and I have some other point over here. That's not that interesting. I'm only going to be interested in connected spaces. But what's nice about graphs is that anytime you have a graph, there's a natural notion of distance between any 2 points in the graph, which just comes from number of edges. So if I called this point, say, X, and this point, say, Y, I can do the same definition I did before. I can say dxy, and if this is the infimum, in this case, it'll just be a minimum over all gammas connecting x to y, the length of gamma, where this length function is just the number of edges in the path. Okay, so if I wanted to go from x to y, here, it's pretty easy. We can say distance between x and y equals 1. Suppose I wanted to connect some different points. Let's say I wanted to connect z and w, the distance between z and w. Well, let's see, what paths can we choose? We could go like this. We could go 1, 2, 3, 4, or we could go 1, 2, 3, and I think 3 is the best we could do. We get 3. Okay, so there's a natural way to mention distance, and with this comes a notion of a neighborhood. So let's just draw a graph for a second. I'm going to draw kind of a small one, but with a few more edges. Okay, let's just put some edges in here. Okay, so let's say I pick a particular vertex and I said, I want to identify the ball of radius 1 around this. Well, that's just in the usual definition of a ball applies. What are all the things you can reach in a path of with distance less than or equal to 1? So the ball around my vertex x of radius 1 is just going to include what? Well, I can get to this vertex with path of length 1, this one, and this one, and this one, but every other vertex in my set takes a longer distance. Now, I can change this pretty quickly. Like if I put in an extra edge like that, then this thing gets included in my path of it as an element of distance 1. So the actual combinatorics of the graph really matter. It's not expecting this to match the distance of how it's embedded in the plane. Okay, does this make sense? Okay, and where am I going with this? Once we have a notion of distances, we can talk about thin triangles, okay? So we have this definition you've already seen due to Gromov, that a space is delta hyperbolic if every triangle is delta thin. And here's a particular kind of graph that's always delta hyperbolic. So a tree is a graph with no loops. So let's put in, this is not a tree, okay? Because we have this loop right here, okay? So that's what tells us it's not a tree, but if I put in even something with lots and lots of branching, it can be an interesting graph. It doesn't have to be a boring graph. It just can't have any loops. This is an example of a tree. Okay. And so my question is, I've given this claim below that says every tree is delta hyperbolic. What's my question? My question is for delta equals what? So what's the claim I'm making is, first of all, that we can think about what a triangle is in a graph in the same way we've been thinking about it previously. So I pick 3 vertices in my graph, and I have to connect each of them by a shortest path. Well, let's actually do this on here. So let's take this vertex, say, and this vertex, and this vertex, okay? And let's find the shortest path between each pair of these, okay? So I'm gonna try to do each of these shortest paths in a different color so we can see what they are, okay? So here's the shortest path between those two. Here's a shortest path between those two. And what's my shortest path between the ones I haven't yet connected? Like, how do I get from this one to this one?
Concatenation of the 2 paths.
That's right. And why do I have to use concatenation? Well, because I said it was a tree. I said if I choose 2 points, there's only one way to get between them that doesn't involve backtracking. Okay? So I've claimed that every tree is delta hyperbolic for delta equals
Zero.
0. Fantastic. For delta equals 0. Because we're saying that any edge is actually contained in the union of the other 2 edges. Every edge in every triangle is contained in the union of the other 2 edges. Okay. So what would graph look like that's, say, one hyperbolic? It doesn't have to be a tree. If it's a tree, it's 0 hyperbolic. But if it's one hyperbolic, what might that look like? I don't know how I'm asking you to say this, because this is where if we were in a room, I would say, okay, someone come up with chalk and draw me on the board, draw me a one hyperbolic one. Can you guys annotate my slide? If everyone can annotate, someone want to draw me a one hyperbolic tree, a one hyperbolic graph on my slide? I don't know if anyone can.
I don't think we can annotate.
Okay, too bad. All right, so
Yeah.
so maybe hopefully you're scribbling one down on some paper. Let me just try to draw something that's going to be hyperbolic. So if I take something, I'm just going to draw over here, and the idea is something that looks like a tree if you left your glasses at home. Okay, so what am I going to do? Is I'm just going to kind of thicken up a tree. Okay. Okay. So what are you supposed to do? If you left your glasses at home, what might this look like? Well, let's try to do this in highlighter. It might look a little bit like this. It's kind of going, it's going here, and it's going here, and it's going here. And that purple thing looks like it would be a tree, right? There's no loops in the purple thing. But that purple thing is covering some smaller loops in my black thing, okay? And so what comes out of this idea is the idea of coarse geometry. So saying that a graph is a tree is an extremely precise statement. It's saying that there's no loops. Saying a graph is delta hyperbolic is saying, well, we're allowing some amount of error. It's like the difference between being Lipschitz and being continuous. It's not the same thing, but it's along those lines. It's saying we're not going to require something as strict as being a tree, but we still want to capture this. So the idea of coarse geometry up to some error, so geometric properties with some tolerance, is something that shows up all over the place in my research area in low dimensional topology. So we've done a pretty massive escalation in sophistication from taking some path integrals in R2 to get line segments to now talking about coarse geometry of graphs. But I only have a couple minutes left, and I just want to give you a few quick tastes of where this kind of thing comes up in the research world. Okay, so for a complete change of topic, one of the other areas that something like this can come up is if you have what you sort of naturally have is a continuous surface, but what we've done is you've turned it into a discrete surface. So computer graphics, the world of computer graphics doesn't really like doing continuous thing. It's way too much data to try to consider, but it's very happy with discrete data. So if you want to capture an image in a graphics world, one of the things you might do is you might take a mesh, associative image. So you sample some number of points on the surface, you connect some of them by line segments so that you get something like this. This is a pretty coarse mesh of a dolphin. And then that's only information that's stored. And you have some process that says when you take this mesh data, this graph, and you reconstruct it, then this tells you have some process for you how you layer on a texture or something like this. And this is how you reconstruct an image or how you save the data of an image. And one of the things that's interesting about this is that maybe you want to analyze an image. Maybe you're trying to do facial recognition, or you're trying to do these kinds of things where you say, okay, I'm going to give you have you seen these ones where it's like a picture of a dog or a donut? You have to try to figure out which one, or like cheese or a rabbit or something like this. Like, how do you tell the features of an object from a mesh? This is something our brains are really good at doing, and it's an ongoing problem to try to train computers to do this. And one of the things that's interesting is that if you're trying to study a hand, for example, areas of where joints are tend to have hyperbolic curvature. So take your hand for a second and look at like a joint of your finger. If you trace it around in the direction like if you had a ring over your knuckle, you have a curve going this way. And if you trace around in the bend of your finger the other way, you have a curve going the other direction. So my picture that I'm having in mind right here is, this is my finger. Okay, it's not so great, but that's a finger. And what we're supposed to do is I'm supposed to compare that curve with that curve. And we're supposed to say, that's actually a hyperbolic point where I have one curve going this way, going up, and a curve sort of transverse to it, curving in the opposite direction. Okay, not the best finger in the world. That's like a fingernail. Okay, that's my finger. So one of the things that shows up in computer systems which are trying to recognize things from from mesh pictures is that recognizing points where there's negative curvature helps them recognizing things like joints or features where something interesting is happening. I'm using interesting in a very vague way, but if you look, for example, at these where the flippers join here, we see that same kind of thing, like where a finger's joining. Okay, so this is something that's actually used in a very practical way. You take your mesh, you have some rules for how you're sampling, and then you identify important features of your object by looking at where the delta constant can be made small to be delta hyperbolic. And then the very last thing, because I'm a low dimensional topologist, I want to end with something straight out of pure mathematics, is I want to give you a brief introduction to one of my favorite graphs. So this is an infinite graph, okay? And this is a graph called the curve complex. So what we do to define this is we start by we fix some surface, okay? And I'm going to use this surface to define a graph, okay? And what is my rule? Well, my vertices of my graph are going to correspond to classes of loops on the surface that don't intersect themselves, okay? So here, I have a loop like that. Let's call that loop A. Let me change colors for a second, okay? That's A. I'm going to have a loop that goes like this. This is B. Let's have this loop over here. This is my C, and maybe let's put one more in. Let's put in D down here, okay? So on a given surface, we're going to rule out some really simple things like spheres, just the torus. So let's assume we have a surface that has some sufficient complexity. We're going to have a vertex associated to each. This is called an isotopy class of simple closed curves. And we're allowed to wiggle these. So when I draw this curve here, this red curve, if I drew this curve, that's the same, okay? So we're looking at, but if you think of this as a string that's laid onto the surface, if you can slide the string along the surface, then and get it to a different representative, that's just the same vertex. So that's why I'm calling them deformation classes of loops here, okay? And so this gives us our vertex set. And what we want to do is we want to figure out when we should put an edge in, because we want to turn this into a graph. And our rule is that if you can deform two curves in these allowable ways, sliding them along the surface so that they don't intersect each other, then we put an edge between them. So if we look at this here, we notice that as drawn, the orange and the green curves are disjoint from each other. So we put an edge in here. We also see that the orange and the red curves are disjoint from each other. So we put an edge in here. And the red and the blue curves are disjoint from each other. And we put in an edge here. And we see that the blue curve intersects the green and the orange ones as drawn. And then you have to convince yourself that there's no way you can deform it to eliminate that intersection. So it's not necessarily obvious at first glance how you might do this, but what I want you to believe is that this is a well-defined object, okay? So this is a thing one can define. And a cool theorem that was proved maybe when I was an early grad student was that this thing is delta hyperbolic. So it's an infinite graph. There's infinitely many vertices. It's infinite diameter, meaning for any real number you give me, I can find two vertices where the shortest path exceeds that number. But in fact, it's delta hyperbolic. So it turns out that this is actually a useful tool for studying all sorts of things. A little bit hard to motivate right now, but I just want to sort of point out that this idea shows up in all different parts of mathematics. So hyperbolic geometry or negatively curved spaces make sense in any dimension. I've only been talking about the surface case, maybe a little bit the graph case here, you can see some other dimensionality. In 3 dimensions, which is where I spend most of my time as a researcher, it's a reasonable statement to say that most 3-dimensional spaces are hyperbolic. And because of this, a lot of interesting and important theorems are proven once you prove the hyperbolic case. So sort of all the things that aren't hyperbolic are easier or somehow special cases. And then if you really want to tackle the hard cases, you have to tackle the hyperbolic case. So maybe the most famous example of this is perhaps you've heard of the Poincare conjecture or the geometrization conjecture. So this was really famous open problems. There's $1 million bounty assigned to the Poincare conjecture. And of the 7 Millennium Prizes that each were given a $1 million bounty, this is the only one where the problem's actually been solved. It hasn't exactly been claimed because the person who solved it's a bit of an eccentric guy and he decided not to choose to accept the prize, but it's still kind of a cool little tidbit that's out there. So especially here at the end of the talk, I've just been trying to point out some interesting things for exposure. If anyone wants to hear more about them, I'm happy to chat either in person when I have an office again, or over Zoom, or send me an email. And otherwise, thanks so much for your attention. And yeah, go to the vaccine. Thanks.
Thank you so much, Joan. That was a really great talk. Does anyone have any questions they'd like to ask Joan while we still have her?
I have a question, if
Yeah,
I can
please.
ask. So we define the triangle as the shortest path connecting three points.
Mhm.
Is there any case, some really weird plan, the shortest path is not unique, and then when that happens, what happens to the triangle?
Sure. So we can even do this in one of the sort of the cases we've already seen here. So let's suppose we're on a sphere. If I give you two poles here, then you have the shortest paths are equally given by the two arcs of this great circle. So like this little front arc and this little back arc, those are the same length. Okay, so there's absolutely no requirement that the shortest path be unique in the full generality of how I stated things. Now, what we're really doing here is we're trying to understand a situation in which we can define a distance between 2 points based on measuring the lengths of shortest paths. And I sort of casually use the word geodesic. If you're a differential geometer, that might have made you cringe a little, because the geodesic is usually something that's only locally minimizing length, not globally. If you want to take all of the things I've described as sort of properties and apply them to any particular setting, you might want to be careful about when you have uniqueness, when you whether a different choice of paths would give you a different kind of structure. But you can always put more hypotheses on your space so that the question still makes sense. So great to point out that shortest path is not necessarily unique.
Yeah, cool. Thank you.
Any more questions?
Recommendations for further reading. So let me think, what's the best thing? So there's a lot of fun stuff out there. Maybe what I could do is, Thomas, if I send you guys a couple of links for resources, can you post them with the talk announcement?
Yep, absolutely.
Okay, let me do that, so that way I can do it thoughtfully. I mean, there's a book by Francis Bonahan on hyperbolic geometry that I think is a really good one. It's been used as a basis for classes here before, a class that's not taught anymore. But there's other things that are sort of lighter. So I'll try to put a range of different things that might be require different levels of commitment.
Any more? I'll ask one question. If someone wanted to look into more of this in an ANU course, is there any particular thing you'd recommend they need as background, or?
Great question. So I think, my bias is that analysis 1 and algebra 1 are the gateways to sort of all the fun stuff. So again, you're getting very much my angle on these things, but differential geometry is certainly one of the classes where some of these ideas are going to show up, and algebraic topology is the other one that starts to see properly understanding, where do things like this come from? What's the right relationship between the plane and rolling it up into a torus, so on. So I think those are the two classes to kind of have in your sights. There's also a variety of topics classes that pop up here and there. I've taught reading classes on hyperbolic geometry. Vanessa Robbins and Kate Turner have taught combinatorial or algorithmic topology classes that have picked up some of these ideas, things like studying structures of combinatorial complexes. So one step more sophisticated than graphs. When do you fill in faces, things like that. I think those are probably the main ones. And the other thing I should say, I'll just advertise, is that I think one of the really great things about the curriculum at ANU is our special topics courses. So if you don't already know about the special topics program, you should set aside 10 a.m. on the first Monday of every semester to come to the special topics meeting and see what's on offer. And if you're ever interested in a topic, get some friends together and get in touch with lecturers and say, please, 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 please teach this. And I think that this hit rate is pretty high for getting good responses for that.
Awesome. Thank you much. And thank you to everyone for coming as well to the first of our seminars in the series. We'll send out a link to the lecture and those resources we get from Joan. And yeah, thank you all again. Stay safe.
Thanks so much, everybody. Take care.